Sketching composite functions isn't very much different from sketching rational functions. It's just a different kind of function. The processes associated with it are really just the same things. So we're going to analyze and graph this particular function that I have given you here. Just like with rational functions, we're going to analyze that original function. We're going to look for information related to the domain. Now, I know that I cannot square root a negative number, so that means my x squared minus 4 has to be greater than or equal to 0. So that's what I have written right here. I factored that, and I thought about, well, that is really just the same thing as the parabola with a vertex at 0, -4, opening up, and its x-intercepts at -2 and +2. That function's always positive when x is greater than +2 and less than -2. So x is less than -2, or x is greater than or equal to +2. So that's the domain that I have written here. So our domain is the set of x such that x has to be less than or equal to 2, x is greater than or equal to 2. I also want to look for my x and y intercepts. So I started with my y-intercept. I would have to let x equal 0. Now, that should have been a clue right there that that's going to be a problem because that does not fit into our domain, so there really isn't going to be a y-intercept. However, if you didn't realize that, you could plop that in there, and of course you get the square root of -4, which in the real number system is undefined, so there's no y-intercept happening here. And then I checked for x-intercepts by letting y equal 0. So I let my y equal 0, I solved that for x, x is plus or minus 2. So on my graph over here I have -2 plotted and +2 plotted. All right, so I've analyzed that original function. Now, there's no asymptotes in this question. It's not like a rational function that way, but if it was a composite function where I did possibly have some asymptotes, I would also need to consider that there too. Now I want to look at that first derivative and analyze that first derivative. So I rewrote my original function with an exponent rather than the square root sign, and then I used my chain rule, brought the exponent down front, the bracket as it is, reduce the exponent by 1 whole, and then times the derivative of what's inside. And I simplified that. I would have 2x over the 2 on the bottom, and then I just changed the exponent -1/2 to the bottom and made it a square root sign again. And then I reduced my 2's and made that an x over the square root of x squared minus 4. Now this first derivative is undefined for any value of x between -2 and +2, so I need to keep that in mind. So for my critical numbers, I'm going to let that first derivative equal 0, and I get x equals 0, but that's not in my domain, so there's no critical numbers, but I can still check for my intervals of increase and decrease. I can use that domain and look at when x is less than -2 and when x is greater than -2. And then check the value of the sign of the first derivative to know whether my function is actually decreasing or increasing on those intervals. So I figured out that it was decreasing when x was less than -2 and increasing when x is greater than 2. So I know my function, if I go to my graph here, my function has to be decreasing, so it has to be heading downwards here, and when x is greater than 2, it has to be increasing, so it's heading upwards there. So I'm keeping that in mind when I go to do my graph. All right, now we're going to analyze the second derivative here. There we kind of go. There we are. So I've got my first derivative written right here. I'm going to need to apply the product rule. So I took the derivative of the first, the derivative of x is just 1, times the second, plus the derivative of the second is all of this, using the chain rule with that, times the first. And then I simplified. I factored by pulling out that lowest power of the x squared minus 4, which was common. And it left me with f double prime at x being equal to this. And our second derivative is undefined for any value of x between -2 and +2. For possible points of inflection, that second derivative has to equal 0. If I set it equal to 0, I get this untrue statement when I try to solve for that. So that means there's no possible point of inflection. I'm still going to check my intervals of concavity on my intervals in my domain. And when I check that, it's concave down for both of those intervals. So Now I'm going to put all these pieces together here. So my function, when x is less than -2, my function has to be decreasing and it has to be concave down. So I'm thinking it might look something like that. And my, let me just undo that for a second. There we go. I'm going to do it in a different color because I already used the blue to help me kind of define some things. So I'm thinking my graph is concave down and heading that direction, and it has a closed circle there because equaling 0 is okay for the original function. X can equal -2, my y can equal 0 there, and this is +2. I have to be increasing as my blue arrow indicates, but I also have to be concave down, so I'm thinking I'm heading that direction. So I have that mirrored image over the y-axis there. And there's my graph for my function f at x, which I'll just label as f at x there. So the blue is not part of the graph here. That was just to help me remember what it was I found about the first derivative. Hopefully you remember those processes in terms of using steps for graphing, and good luck with your questions.